And welcome everybody to GDG Lawrence, week 5 of the Professional Machine Learning Engineer Study Group. My name is Roman Jaquez. I am one of the lead organizers at GDG Lawrence. Today also we have an amazing speaker. She's going to be honoring us with her presence and her knowledge. So you guys are in for a treat. Again, just wanted to let you know this is again a study group that we've been holding for past actually more than a month already, and we're like into the second month, and now we're going to be holding week 5 of this professional machine engineering certification study group towards getting the certification. So let me just go through a couple of slides, and then we're going to start diving right in. So again, just wanted to thank again to all the co-hosting chapters, GDG Cloud Boston, like I mentioned, Norbert right here in the house, Roya also from GDG Cloud Boston, GDG Capital Region. Thank you, Linda. GDG Ocala, GDG Tampa Bay, Space Coast, Modesto, Surrey, a lot of places all over the place. Again, this is not like a one-person show. This is a collaborative effort. So thank you, everybody, all the co-hosting chapters, and bringing your communities along. Again, we are a little bit far already into this journey, so we are at week 5. If you see this table right now, you should be at week 5. I've even gotten the question like, am I too late to join? I say still join, at least so that you can get a feel for how these study groups are. But other than that, you can join any other sessions. I definitely invite everybody to join some of the other neighboring communities study groups. Norbert's with his database engineer certification, some of the other certifications in other groups, but yeah, you still can join. But again, if you really want to get this certification, you're in for a tall order. But anyway, so you should be at week 5. Week 5 deals with natural language processing, NLP, on the Google Cloud, and one of my favorite topics, recommendation systems on GCP. So this is a pretty cool topic. So again, remember, this is an overview. For those of you who already did week 5, this will be just a review. For those of you who haven't tackled it, it will be a preview of what you will see. Remember, it will only have 1 hour. We have Roya's time and her presence. So let's definitely take advantage of that. Make sure to join our raffle at the end of this session. At the end of this session, we're going to be raffling one item from the Google store. I'm going to be dropping the link to the link to that on the chat right now. It's either whatever you have on the screen or this form right now. Make sure to get it. I think I can also give you the both forms, the actual link and the tiny URL one. They're both the same. Make sure to put your name in it. At the end, we're going to be raffling one of these items from the Google store, from the Google merchandise store. So just as a token of our appreciation, add your name to the form. We're going to raffle it at the end. Again, like I mentioned, put your name in there. Thank you so much. And without further ado, Roya is going to honor us with, again, the review for this week's content, week 5, talking about natural language processing, NLP, and recommendation systems. So I'm going to stop sharing. I believe Roya is already in there. I was going to make sure that Roya has access to the screen. So I believe you do have presenter mode. Please go ahead. And without further ado, Roya.
Perfect. Thank you very much. Thank you all for having me here. Thank you for the invite. I'm Roya. My name means a very sweet dream, and I studied in electrical engineering. Right now, I'm working as a research scientist in the scope of generative AI. I'm also a GDE in Gen AI, a cloud champion, a WTM, and also, as was mentioned, a co-organizer with GDG Cloud Boston. Because we only have less than an hour, I try to dive in quickly. Uh, so the first piece would be about natural language processing, and I try to make it more toward what are the content, but also to give you a little bit of background how to deal with it. Uh, the first question is, what is natural language processing? Before I start, a huge shout out to Melody Jung for helping me with this slide. Natural language processing, the idea comes from if we are able to generate a meaning for a sentence. So if I give you this sentence of I love my dog, uh, what we are trying to achieve with natural language processing is that we wanted to be able to say whether this sentence is positive or negative. But it is a really complex problem to teach the machine what are basically what is the meaning of this sentence, right? So let's dive into how we can generate a numeric representation for these words to be able to see uh, from a computer perspective, computationally, what does that mean? Uh, the first thing that comes to mind is we can do character encoding. So you all know about the ASCII code. Suppose we have some word like listen. If we put the ASCII code of each of these letters together, uh, something like this would be achieved. It makes sense. We have some numbers and we might be able to build a system to turn to these numbers to identify what was the meaning of this word. So essentially, we're associating some numbers to the meaning. But if we just switch some of these words, then we will see that just by switching these letters, we get an absolutely different meaning. I would argue that listen and silent are quite the opposite. So it puts us in a difficult position because right now we cannot actually get these numbers and enable the system to identify what was the meaning. Uh, so what should we do? What if we get each word a number value? So by that, what I mean is, let's say I gets the value of 1, love gets the value of 2, my gets the value of 3, and dog gets the value of 4. So far, so good, right? Then if we have a new word, let's say cat, then we are adding a new number to that. So still I is 1, love is 2, my is 3, but cat would be 5, right? Makes sense? Okay. If we keep doing that, we can generate a corpus of the information. And this corpus would be a collection of all of the machine readable text that we want to be able to identify later on. We put all of them together, every available sentence, and we build a vocabulary dictionary that connects a word to a number. With that, we are building this dictionary that we can later on go back and forth and identify what number represents what word. Before I move on, if there is any question up to this point, let me know. I'm reading all of the chat, so if there is questions or there is not. Okay. If we look back in the history, up to this point, we were able to solve the problem of representing a word with numbers. But we are still distant from identifying whether a sentence such as I love my dog is positive or negative. Back in time, to enable us to solve this problem, feature engineer would sit together and identify what words are associated with a positive sentence and what words are associated with a negative sentence. The two figure on this slide, they're supposed to show this concept of bag of words. So each bag holds the words that are associated with positivity and negativity. And I think even today we don't have uh, a image generative machine that is able to actually spell things right. So if the spelling on these generated images is not right, it's because of the I think the shortcomings of this Gen AI system. But as they show, so for example, we associate joy, happy, wonderful, and peace with something being positive, and awful, sad, angry, and hateful would be associated with negative. This makes identifying positivity and negativity a little bit hard because then you have this contradictory system of language. For example, it's not good, which means it's not good, but because it has the word good in it, we still associated it with positivity. So it brings us some challenges because now we have issues with identifying the sentiment. A step further from this bag of word was the idea of embedding. And one of the classic methods of showcasing embedding is by this visual representation. The idea of embedding essentially is that we associated each word with a position, with a location in a multidimensional space, that the position and the distance from the origin, both of those have value and impact in the in the meaning of that word. So for example, if we have a spectrum of niceness, then kind and nice and their respective position on that spectrum actually represent meaning and value to how we perceive this value, how we perceive this word. So now I want you to think about a two-dimensional grid. One of these grids is royalty, and the other one is being a man. And if we think about that with all due respect to people who are identified as uh, any gender, we think about this spectrum as one side of it being women and the other side being men, and then everything in between falls in the middle of this spectrum. So, with that definition, if we have the word king in this grid, we should have one essentially unit up toward royalty and one unit right toward being a man. So the location of one and one should represent a king. Now, if I ask you where man should be in this grid, then I think it's reasonable to think that we should subtract the royalty value from a king value and then achieve to a man value. With that definition, a man would be the man would be located at one unit right, but on the essentially origin of the royalty. So if we have queen, then we want to keep the royalty, but we want to remove being a man. So it would be located on one unit up in the royalty measure, and then we do not want to give anything in the manness essentially a spectrum, so it stays on the origin in respect to the horizontal axis. And lastly, women are at the origin with no royalty and not being a man. I hope that you find it so far so good. If there is any question, I pause for a second and please put the question in the chat. Okay. So with that being said, we are able to actually do a mathematical equation. So we can, for example, subtract royalty or madness from
Sorry, go ahead.
no worries. I don't know how long I've been on.
No, just for a second. Just for a second. I've been taking care of things in the bag. No worry. Please continue.
Perfect. Thank you so much. I appreciate that. Sorry, I was mentioning that right. So given these embeddings, we are able to actually build arithmetic equations between these values. So for example, if we add one unit of being a man to a woman, we reach to a man, or if we do the same thing to a queen, then we reach to the position of a king, right? And that's also showing on the grid on the right. It also enables us it also enables us to go to play with the royalty, and then, for example, go from a woman to a queen or from a man to a king. We can represent these values and feed them to the machine, and the intensity of these values also essentially have meaning, because we can, for example, define a prince, we can define non-binary individuals, and each of them would fall into their respective location on this grid. What it brings us is that now we can generate a structure that puts similar words close to each other. So one of our friends is asking if this is just a clustering system. You can apply this to cluster information. So essentially, you are clustering um, words that have similar meaning to each other, but simply because the value and the intensity of each of those words in their respective position have meaning, it adds more to that clustering, because you can't build arithmetic and then go from one word to the other word, or have negative meaning, so that's not good. It's not a problem anymore. But still, we have issues to go from these words to meaning that a sentence would bring. So I want to take you back to where we were talking about the neural networks. So in a feed-forward set network, we have all of these input values, and then they go towards some hidden states, which are shown here by the red, and then we eventually get to some outputs. For the simplicity of what I'm going to discuss next, I will squeeze this whole thing into this one box, and that blue box would represent a feed forward network. And then we can just show it in the vertical mode to make it more visually aesthetically pleasing. What is happening when we are dealing with neural network for words is that we would lose the importance of sequences. If I just show you an image of a ball, it's really hard for you to guess which way this ball would go, right? But if I give you a snippet of a video of which side this ball is coming from, then you have information to decide which way that ball would go. The idea of sequences in neural network is not just about deciding which way the motion goes or about the words, but it has many applications in any type of scenario which you have a sequence. Anything such as a stock market, weather, or any other topic that you can build a sequence, you want to include that dimension of like sequence and temporal information into your data. And that goes for natural language too, because now each word and the surrounding word around it actually impact their meaning. So to enable our system to look into a bunch of words, we can apply each word x1, x0, and x2 to a different feed-forward neural network and expect the system to identify what is the best next word. What we are missing here is that we are not incorporating any notion of the sequence that we are dealing with. To fix that problem, for essentially dealing with sentences which have the idea of sequence, we introduce this new parameter called h, that is the prior state of the system that would be fed to the next state. I don't know how many of you or if it would be possible, maybe a raise of hand on how many of you have heard about the Markov chains. Perfect. Thank you. I have a few hands up. The idea of Markov chain, I think, is the essential essence of what we are trying to do with recurrent neural network. If you have heard about Markov chain, you know that the state of system is not only depending on what is currently happening, but on something that was previously happened, right? A good example is, think about somebody doing you wrong. If it's the first time, you might let it slip. But if it's been a repetitive act, your punishment, the punishment that you think about for that act, might not really uh, m- f- be just for that act itself, but you have all of those memories of everything else that has been done wrong to you, and then that punishment might be exponentially bigger because you are considering what happened in the previous time. In here we are, thank you, the straw that breaks the camel's back, exactly. uh, the idea that we are here trying to implement is to bring the notion of what was happening in the past to make a decision about what is going on in the future. And that's different from just a feed forward network that takes into account the current input and generates the current output. So now, when we are feeding the system the x0, which is something that was happening in the past, and we are generating y0, which is the output for that specific input, we are getting a snapshot of that output and feeding it to the next time step, which is x1, and be including both of these values as input to the system to generate the corresponding output. And that goes on and on based on the length of the system sequence that we are dealing with. It adds another important, I think, capability, because if we were not to do this, we were limited by the size of data that we are feeding to our system, right? Because then we had to have a specific size of matrices. I assume that in this series of courses you went across convolutional neural network, the specific type of architecture that goes over images. And I assume if you went through the courses and the labs, you had that a snippet of code that forces you to adjust the size of the image that you are feeding to your network. For example, your network only can get input from the size of 128 by 128. And the reason for that is, underneath of all of these neural network, these are fancy matrix manipulation. And the size of those matrices has to stay similar to each other. We cannot modify them after training. If the size of our sentence changes and we have to change the size of the input, then natural language processing would be doomed. We could not constantly have a dynamic matrix. But with this specific type of architecture, we can feed in as much of an input that we can feed to the system, and then we keep the rest of it for the next snapshot. So not only we are making the best out of the size of the memory and the system that we have, we also taking into account what is happening in this sequence. I pause for a second to make sure that there is no question.
There's only one question in the QA. It says, I think it referred to maybe something that you were discussing before. Pavel says, so it's simply just the clustering. This may be related to, some of the topics you were mentioning before.
I talked about that, and as I mentioned, the idea of embedding enables us to be able to cluster words with similar meaning, but it's because of the intensity and the value of each word, it gives us way more than just clustering. If there's no other question, I continue. So when we are, as I mentioned, when we have these neurons with the recurrence, the input to the system is not just what is the current input, but the past memory, and then we generate the output. And just for of representation, if you read a paper or an article, you would see that there is this like loop around the recurrence cell to showcase the state of the model. An issue that is really um, prevalent with recurrence neural network, and it's similar architecture is exploding gradients. These models tend to have gradients that grows to a point that you get infinity in your weight matrix and the model stops growing. In those scenarios, it's been advised, it's the best practice to apply a clipping gradient, which essentially forces your weights not to be adjusted too much from their initial value. There are also the opposite problem. We have the vanishing gradient because when we have this recurrent neural network, we have still this back propagation in the system. And because we are going further and further in the system, so these systems are really deep, the gradients after a while would be too small that essentially doesn't have any impact. Uh, this was mainly a problem when people were using TANH instead of ReLU, and the invention of ReLU was as an activation function solve this problem very much. We also can do weight initialization to make sure that the weight is further from the identity matrix that was the initial weight setting. And lastly, we there are new different type of architecture like LSTM, that is long short-term memory, that enables the system to not only keep what is happening right now but have a notion of what was happening in the past, essentially passing the important information from current to the past. So with this long-term memory dependency, we are able to hold information from the very past, not just immediate past, for the future when we are talking about those. And long short-term memory, I don't want to get really deep into that, but it has a mathematical structure that is able to hold on to the important information and leave what was not really important. So it keeps and passes the important gradient to the back. So far, so good. Any questions? Okay. I talked about recurrent neural network, gated neural network, and LSTM because I wanted you to ask me this question, that why we can do what we can do right now if dealing with natural language processing is such a huge mess and problem. The reason that we are able to do what we can do today, and by that I mean uh, being able to feed 1.4 million words into our system, is because of the concept of attention. Everything that we are able to do in computer science is because we are able to make a mathematical formulation of how we think about something as human, to teach it to computers, right? So this whole structure of neural network came from how we are thinking and how the synapses in our brain works and how they pass information. The idea of attention comes from how we are thinking about words and the word's location in a sentence. So, in a very simple word, imagine that we have a grid, that in one side of this grid we have a fruitiness, and that would be the right top side of this grid. And all of the electronics would happen to be at the origin. So reasonably, we expect strawberry and orange to stay with the other fruits, and phone and Microsoft to stay with all of the other technologies. Now, if we have a new word, suppose cherry, we expect it to sit by the other words. And if we have Android, we expect it to sit with other technologies. I bet you are thinking, what about something such as Apple? Because Apple has an ambiguous uh, meaning, because it can be an apple as a fruit or it can be an apple as in a technology. We want the apple that represents a piece of fruit to stay with other fruits, and the apple that is a technology to stay with the technologies. But in reality, when you just train the embeddings, both these words stay in the middle, because essentially they draw off both of these location would be similar, so the system, no matter how many times you are training it, keeps them in a middle. What is the solution? We go back to how we think about this concept as human. If I ask you to buy me an apple and orange, most probably you will buy some apple fruit and some oranges. There is no way that if I ask somebody to get me apples and orange, he come with a iPhone and a box of like a packet of oranges. And if I say Apple released a new phone, we simply know that the Apple here means the Apple company. We are building a grid of information based on the other words that are existence in the system. And that's how we pay attention and make sense based on the context. Now, the idea of attention is exactly formulation of the same concept. So instead of just building this embedding based on the meaning of this word, we are building this embedding in a grid that also incorporates other words into the system. And it enables a system of gravity that when the word apple and the word orange appear together, we actually, the embedding location, the position of that word in the latent space would be closer to the orange. And the same goes with when we have Apple and the phone company. Before I end with the natural language processing, is there any question? Because I'm moving on to recommendation system next.
Able to see them.
Yes,
I
actually, I
dropped
just
one
saw
from
them.
the, yeah, if you don't mind taking a look at those.
Uh, is it 1.4 billion words or 1.4 billion Unicode character? I misspoke. If I said billion, I meant 1.4 million. Uh, Gemini Pro right now is able to hold 2 million tokens, and 2 million tokens is almost 1.4 million words. And to give you a essentially a way to compare, all of the 7 books of Harry Potter is 1.1 million words. So with this current Gemini that is accessible to public, you can feed all 7 books of Harry Potter to the system and ask question. Where should we apply the vanishing or expanding gradient? Comparing with vanishing, we know that slopes decrease gradually to a very small value compared with exponential growth of the slope. So why and when we should use it? So with the vanishing gradient, you would see that your system stay unchanged and the weight would not change any further. Right now, except for if you are dealing with time series analysis, it is not the best practice to use recurrent neural network for natural language processing, but these are in Keras, which is a library for deep learning. You can find both of them. You can add a gradient clipping the same way that you add an LES stopping to any of your layers, and you can also add gradient vanishing, so you can apply basically the random value to your layers. Uh, Key question, is the intensity and value with memory similar to the ChatGPT memory control feature they released earlier this year? I am hesitant to think they are the same thing. I did not play with ChatGPT memory control enough, but I assume that it deals more with the number of token, whereas what I'm talking about is the type of embedding that we are dealing with. Uh, is it good definition for what is a good definition for attention? Um, I think I try to define it. It's a mathematic formulation of how we as human make sense of words based on the context of the words around them. And I hope that satisfy you. I assume there is no other question. Thank you for showing Bert. As I mentioned, what I'm saying here is really uh, basically a bird's eye view. I thought it's more interesting to go a little bit deeper into the background because you have a lot of content to go through throughout the courses. Uh, and that should give you information about something, for example, like BERT, about GPT, what are the differences, what happened with Palm, what are the best practices right now. If that's something that interests you, if you want me to go deeper, for example, into the architecture of attention, the architecture of BERT, or anything else, the transformers, please let the organizer know, and I would be more than happy to prepare a session that is a more deep dive. The next topic to discuss is the recommendation system. And similar to Roman, those are very interesting to me because of I love mathematics, obviously, and they are mainly math that led to really interesting ideas in neural network. By definition, recommendation systems are machine learning tools that enables us to make suggestion based on what the user past interaction was, based on the feature of the object, and also based on the similarities between different users. These are really cool concepts, but I need to warn you that they are also responsible for the digital silos that we get stuck into. When you wanted to, uh, for example, recommend a vacation house to somebody, you can look into all of the houses and all of the houses that one person looked into them previously, and then how you can match that person, and if you can find similarities between two of your users. So you can look into, as I mentioned, the properties of that user, the properties of that house, the properties of the houses that user rented previously, or who rented that specific house previously. You also can look into different users and how they are similar to each other, and look into different items and see how they are similar to each other. Historically, it requires us to do a lot of feature engineering to define what defines a user, what defines a house, and then going across, for example, different houses and figuring out what is close between two houses. I don't know if you ever looked into Zillow. It's a platform to find houses for purchase. And then when you choose a house, it asks you, what about this house made you interested in this, right? And then it looks into what you choose and it brings it as an explicit feedback, and then gives more value to houses that have the similar characteristics. That is a recommendation system built underneath, and somebody sat down and figured out what features in a house can be appealing to any users. And then obviously based on your reaction and how you are interacting with your uh, searches, they get information about the house. Your previous rental or previous purchases, or what you liked in the system, information about your previous behavior. And the system also has information about who has rented a house previously. The easiest part is to find similarity between two users or two different items because they already showed a lot of interest, or we have all of this information about the items. I see something in the chat. Yes, Zillow. I don't know if I guess in the US it's really common, but if you are not based in the US, I don't know what is a similar thing. But you can think about Netflix or any retail essentially uses these recommendation system underneath to suggest you what is the next best thing that you can purchase. There are three major recommendation systems. We have content-based recommendation system, we have collaborative filtering, and we have knowledge base. So content-based recommendation system is essentially recommends item to the user based on how they interacted with the system and what features they liked or what categories they liked. So, for example, if you go to YouTube and look for something, for example, a Persian song, YouTube would take note of that Persian song and then starts recommending more and more Persian songs to you. Persian is my primary language, it's my mother tongue. So, YouTube picked up on that note, and now I get information both in Farsi, in Persian, and in English. The other method is collaborative filtering. So now it is not based on what I chose before, but it's based on essentially the similarities between the items and the similarities between me as a user to somebody else who had similar similarities. So previously, it was looking into the type of option that I choose, right? But now we are choosing based on items that are similar to each other and which user chose together. So if I chose a Persian song before, and YouTube knows that, and YouTube knows that there is some other maybe Persian Tajik speaker, and they chose both of those, now on top of all of the Persian song that I get uh, recommended, I will get some of the Tajik, for example, song or something else that people might associate it with Persian song. And that goes with users that have similar behavior to what I do. So rather than just looking into what I as a user would look like, it would also look like what other user who have similar behavior like me would look like. And lastly is the idea of knowledge-based filtering, and that specifically relies on what a user would look like. And that's if I give a thumbs up to a specific piece of content, for example, on YouTube, or if I say, for example, a house in my Zillow or any other type of product that I'm interested in purchasing or interacting with. Do we have questions? I give it a pause for questions. Okay, I assume there is no question, so let's dive into the last piece. There are major pitfalls with how this recommendation system works. I'll show an example of one of these matrices. But because we are talking about many features and many users, the concept of sparse matrices are really prevalent in this scenario because essentially we have user that might choose one of the million products that are available in a retail website, and then that user is one of a many. So identifying features for them means that we are a few ones, a few values in gigantic matrices. And then we have the skewness, and that means that some of these products would be way more popular, and some of the user might be more interactive with their system, and that skews these matrices toward that specific user or that specific product. A good example is think about Bridgerton. When the first season was essentially streamed through Netflix, everybody was talking about that, and it was not a particular group of users. It was essentially everybody skewed the system to constantly recommend that to all of the user, um, regardless of what they were interested in. uh, Graph database is good for this in a structured word. I want to see how this maps into a graph database. Frankly, I think it stays with matrices rather than graph databases, but I'm not a database person. We have Norbert on the call, and he's a data champion, so I don't want to speak to something that I don't have full knowledge of. Another issue with this is cold start, and that means that we essentially don't have information about some of the user, and sometimes we try to generate some of this information with uh, requesting user to provide us with explicit feedback, asking them to give us a thumbs up or down, or before they start in interacting with the retail, we want them to give us five of the movies that they like, but this is not always accurate because user might change their preferences. In the chat, it's been mentioned that Google is listening to us, and then if you don't have like, I cannot speak to that factually. Um, so the last piece for the recommendation system is this notion of similarity. I mentioned before that we build these embeddings, and then two words in the embedding can stay close to each other if they have similar meaning. I skipped this defining how we mathematically prove this similarity. There are two major mathematical ways to do that. There are other methods, but I stick with these two for the sake of time. One of them is dot product, and for each of those values in the embedding, we are essentially multiplying their corresponding components and summing them. And the other method is the cosine similarity, which it's a normalized essentially dot product, and we just measure the angle between those two. How this is connected to the embedding is that each of these users and each of these product, they essentially build an embedding, and they are represented by a floating point in the multidimensional space. So it matches very well with the idea of natural language processing and how words are represented in a latent space, or quote unquote embedding. If there is no question, let's just work on building one of these embedding. Whereas in the natural language processing, where we train the system to go through these models, to go through the words and figure out which words are close to each other based on their meaning. Here, with building to build a vector to build an embedding, the easiest way is to do feature engineering actually. So suppose we are dealing with six different type of movies, and we had somebody watch all of these six different type of movies and figure out how, if they are fantasy, action, cartoon, drama, or comedy. I try to choose movies that everybody watched, but I hope that it's actually movies that everybody watched. So the first row is Shrek. I think we all agree that it's a cartoon and it's a comedy. The second row is Casablanca, and that's a fully drawn movie. The third row is Harry Potter. We will put it in fantasy and also comedy. Then it's a Star Wars. I've never watched a Star Wars, but apparently it's fantasy, action, and comedy. Then we have The Incredibles. It's action, cartoons, and comedy. And lastly, it's The Black Swan, which is another drama movie. The next step, now we built these feature vectors for all of our items. The next step is to figure out when this person watch movies, how much they like each of these movies, right? So we have this person that previously they looked Shrek and they gave it 7 stars. They watched Casablanca and they gave it 4 stars, and then they watched Harry Potter and they gave it 10 stars. Now it enables us to do an implicit type of feedback from these explicit values and identify how much this person values fantasy, action, cartoon, drama, or comedy. The way we do that is we multiply these implicit feedbacks these explicit feedbacks of ranking of 7, 4, and 10 with these matrices. If you're like me and you see this type of matrix multiplication, you will go and bang your head against the wall. but it's like a row-wise matrix multiplication, because in my mind, the matrix should look right when you are multiplying it. But let's say that we have this mathematical notion that we multiply each row of our ranking with every value in the similar row in our item vectors matrix. So the response would be every place that we had a 1, now we have a 7. And then, for example, for the row 2, everywhere we had a 4, we had a 1, now we have a 4. And with the last row with 10 ranking of 10, everywhere we had a 1, now we have a 10. Now we are able to do a column wise summation. So from the top down, we are putting everything together. So in the row fantasy, we only have 1 10, and it passes to our final vector. We have nothing on action. We have 7 because of the first row in the third column. We have 1 4 in the fourth column, and we have a 7 and a 10 in the comedy column. Uh, just because we wanted to normalize everything, it makes it easier for our system to work with. We normalize the system and we reach to the value of these floating point values. Before I move on, there is a question. How do recommendations get refreshed in real life? I'm glad I don't see the same. I don't know. I think request from 6 months ago. So just wondering. In reality, you are constantly are feeding all of this system with your information. Uh, it's a best practice that when you are not utilizing the system, they will do a concept called federated learning, and they essentially retrain the system of recommendation on your system. So two things happens. One is they are not holding all of your information, so your privacy would be respected, and second is they are utilizing your own system for training the machine, so you are not holding a space on the main platform. But I don't know for a fact if that's what Google does. This is a best practice in the field, so that's what I think they do. I hope that answered your question. uh okay, so now that we built this user vector, which is all of this floating number, we are able to identify what among these other movies that we don't have information about this user might like. So how we do this is we are multiplying the feature vectors of these movies with this user vector that we generated. So for example, uh, if we multiply the first row with this one vector, we have 1 times 0.26, we pass it to our outcome matrix. We have 0 times 1, and that would give us a 0. We have the third and the fourth column that are multiplying by 0, so they pass zeros. And then lastly, for the comedy, we pass the associated number. Same goes for the second row. So we have 0 in the first row, in the second row first column, which 0 multiplying by 0.26 is 0. Now for action, we don't have any value, so that gives us 0, and the rest would be calculated similarly. So if we now sum everything vertically, so we sum all of the values in a row, we will see that this person have a better feeling about watching a Star Wars, and then they would might like watching Incredibles, and lastly, they liked Black Swan. With that, I want to go back in here and just like compare, uh, like get the gut feeling about this. So we saw that fantasy and comedy was present in Harry Potter, and fantasy and comedy is presented in Star Wars. And then this person liked Harry Potter the most, so there is a huge chance that they might like a Star Wars. They gave Shrek 7, and between Shrek and Incredible, we see some similarities, so that comes second as our calculation showed, and they didn't like Casablanca much, so we expect them to not to like Black Swan that much either. With that being said, I think I'm right on time. So if you have any questions, I would be happy to answer them. Otherwise, I pass it to the Roman and Kevin to finish the session.
Thank you, Roya. Thank you so much. I think you were right on time. Again, thank you so much for sharing all your expertise.